Okay, so I'm going to be providing an introduction to quantum information science. So I'm going to aim kind of low in some sense here. I'm going to try to make sure that we pick up the loose ends wherever they may exist for all of you, because I think it's going to be tough to follow the rest of the workshop if you don't have a firm foundation. So if you get too bored with this intro, start working on your origami, is what I'll say, okay? But my assumption here is that we're going to be starting from kind of a PChem or undergraduate level quantum mechanics background. And my goal at the end of these two lectures is to get you to the point where you can read a quantum circuit diagram and understand what the parts are and understand what's going on, the basics, okay? So we'll start with the first thing that you've probably seen in your PChem class or in your quantum mechanics instruction, which is the idea of the Schrodinger equation, the wave equation, for this wave function psi, okay? And here to give you a little refresher, H is the Hamiltonian, which is typically some sort of operator. It might have, for instance, derivatives being taken with respect to spatial variables and things like that. H bar is our kind of Planck's constant here that sets the scale for quantum mechanics, and I is our imaginary unit. The way that we write the wave functions is not unique. So you can write a wave function as an expansion in many different bases, but the point is that it contains all the information that exists about the system here at this level, okay? So even though it's just a function of position, you may recall, you can also learn things about the momentum of the particle from it and things like that, which is a little bit surprising the first time you learn it. Probably the most convenient representation that you'll see is something like this, where we expand our wave function in terms of stationary states. So here we have some kind of an amplitude. This might be a complex valued function of time. We have a stationary state here. So this is an eigenfunction of some Hamiltonian that we deem to be a convenient Hamiltonian to use to write this thing out. And then we have our time dependence here. And the exponent in the time dependence is called the dynamical phase. And this gives us the information about how time evolution works in kind of a convenient form in some sense. But just keep in mind that this is sort of a generic thing that you'll see in a number of different places, and this is going to be useful. Okay. Now, the first thing you learn about the wave function, or the first thing I teach my students about it, is that it's got to be normalized, right? You may recall how that works. So here we're saying that we're going to make this a function of 3 space, right? A function of x, y, and z. And so our normalization means that we're going to have a triple integral here. That's what this d cubed r integral means. Integral over dx, dy, and dz over all space, if you like, okay? And by the way, my slides are available on the shared folder, so you don't have to worry about jotting things down furiously if you're worried about missing something, okay? The interpretation we give to the wave function is called Born's rule, even though Max Born actually got it wrong the first time he wrote it down. This is the probabilistic interpretation of the wave function. So what this says is that the differential probability of finding the system in a configuration that is contained in a volume element d cubed r, centered at position r, is the absolute value squared of the wave function times d cubed r. Okay? So this is psi star psi, right? This psi r absolute value squared. We call that mod squared sometimes, absolute value squared. And this gives us our probabilistic interpretation. And so the normalization, of course, is key to this probabilistic interpretation. Otherwise, it wouldn't make any sense as a probability. So you did the same thing would happen in classical probabilities here. So in terms of that expansion that I wrote down earlier, you can see that these amplitudes here, the C sub j's, also contain the probability information. And here, it's the probability of finding the system in that particular eigenstate, psi j, at time t. Okay? So these are this is the sort of discretized version of this more or less continuous version over here. Okay, so let's do a tangible example that I think folks are familiar with, whether they come from a physics background or a chemistry background, which is our harmonic oscillator. And you know how to write down the wave functions of the harmonic oscillator. I'll do the first excited one just to keep you on your toes a little bit, but it looks something like this, okay? So we have some kind of a function. It turns out this is real valued, although it doesn't have to be. And this gives us our 1D wave function for the harmonic oscillator. You probably even remember what this looks like. It kind of looks like this, okay? So if we think of the probability interpretation, obviously this wouldn't make sense as a probability because this part is negative. To figure out what the probability distribution is, we take the absolute value and we square it, right? And it is clear that the particle is most likely to be found kind of at one of these two peaks here, right? These are the places, the intervals that have the highest probability for the particle being found within the interval, right? And classically, this makes a little bit of sense in terms of a classical state of a harmonic oscillator where you might have a particle oscillating back and forth. These peaks happen more or less at the classical turning points of the thing. Okay, so I'm start something I'm going to call quantum quasi-talk, okay? So the idea here is that when talking about quantum mechanics, you will hear various people make various claims, and sometimes those claims are a little bit dubious. And so for each of these claims that we're going to investigate, we're going to talk about how true it is, how untrue it is. They're all going to have a nugget of truth in them and also some reasons to be skeptical about them. And then I'm going to provide you with my own ranking system of how crazy these are, okay? So here we go. So the first one is that psi is a quantum state. Different functions correspond to different quantum states. This is the type of thing that we say when we teach undergraduates quantum mechanics. Okay? We tell them that psi is the state, okay? However, wave functions are not quantum states, and that's important for us when we start talking about quantum information. You want to appreciate the difference here, okay? So if you're used to thinking of the wave function as being the quantum state, you need to understand that that's not really true. And one of the ways to see that is to look at, for instance, our position space wave function, which we met earlier, and we figured out how to do the probability distribution. But I could also write a momentum space wave function for the same quantum state, okay? This wave function describes the exact same state as this wave function, but they are obviously different functions. They look a little bit similar because it's the harmonic oscillator, but if you can see that these are actually different. And so this momentum space wave function, even though, again, it looks very similar when we kind of plot it, gives us a different representation of the quantum state than we had over here. So we have two different functions, right? Two different wave functions, but they correspond to the same quantum state. So the important thing here is to realize that the quantum state is kind of an abstract quantity that lives in something called Hilbert space, okay? And the wave function is a representation of the quantum state in, say, for instance, real space or in momentum space or whatever space you may need to use a wave function for, okay? So whatever is convenient. So wave functions are not quantum states. They're just ways of writing, representing them in various convenient ways, okay? So it's an expansion and a basis. So this is my verdict. I give it one theorist beam splitter, okay, which means it's not super wrong. But if you look closely at this diagram, you'll realize this beam splitter does not work the way these arrows say. I call that a theorist beam splitter, okay? And so I'll give it 1 out of 4, all right? It's not super incorrect. It is a little bit incorrect. And the reason I like these is because when you read papers on quantum optics and quantum computing with photons, you will see theorist beam splitters occasionally in the figures. I always think that's hilarious. This photon should go upward, obviously. Okay, all right. And when you're doing your origami, that's important. No theorist beam splitters should be showing when you're done with your origami, okay? That's one of the ways you can check to make sure you got it right. Okay, all right. So continuing on, I mentioned that it's actually, states are actually vectors in something called a Hilbert space, okay? It is a vector space, a linear vector space, and we denote the vectors with this notation here. This is our ket with some kind of a symbol inside it. Here our symbol is A. We also have a different type, kind of dual vector that we call a bra. It corresponds to the same state, but they are mathematically different objects in the sense that every ket has a corresponding bra, but we can tell the difference between kets and bras, okay? It is a linear vector space, so linear combinations are also within the space, right? That's what that means. So I can take any complex number, CA, and any complex number, CB, and I can make another one here, another vector that is in this space, okay? Now Difference between this side over here and what I'm going to call the matrix representation is a little bit like the difference between a quantum state and a wave function, okay? What we're going to do is we're going to take these abstract objects over here and develop another representation of them, but it's a little bit different, okay? So matrix representation, it's going to get a little confusing, but stick with me, we're going to get there, okay? We can represent our kets as column vectors in this matrix representation. And all of these coefficients here, there's a discrete number, we have some number of coefficients here that is non-infinite, and we say that those are, have to be C numbers, okay? The bras are the Hermitian conjugates of the kets. So to remind you what a Hermitian conjugate is, we usually get the symbol superscript dagger is pretty common here. And what we do is you take the transpose, and then you take the complex conjugate of every element. And that's our Hermitian conjugate, okay? And so if I take the Hermitian conjugate of some complex number times a bra here, what I get is the complex conjugate, which has a star, complex conjugate of that number times the transpose of that vector, okay? I mentioned it was a linear vector space. How do we add these things? Well, in our matrix representation, we simply add the column vectors the way you might imagine. Okay, so that's pretty straightforward until you start ending up with something like this. So you have ket A plus bra B. What does that do? Well, now you're trying to add something that is a column vector to something that is a row vector, and that's not going to work. Okay, that's a theorist beam splitter. Okay. So make sure that, if you're doing your algebra, you're working through a problem and you end up with some kind of an expression like this, that's a warning sign for you, okay? Something went wrong. It's a little bit like making a units error or something like that, okay? You want to go back, you want to make sure that you get all that stuff right. Okay, the space that these vectors live in is called Hilbert space. Hilbert space has an inner product, okay? So these vectors have a dot product or an inner product, and we write it using kind of this notation. This is the inner product between the vector A and the vector B. So you always have one bra and one ket when you take an inner product, and the result of an inner product is a complex number. And so you can even take the complex conjugate of it, okay, and you'll get, the same expression with the A and B reversed here. Okay. The inner product of a vector with itself is not a complex number. It is a non-negative real number. Okay? So this is a little bit like the length of the vector. Much like if you had a vector in 3 space, some vector r. If you took r dot r, okay, that tells you information about how long the vector is. Okay? So we can do a matrix representation of our inner product, and here what we do is just what we said. We take the conjugate transpose of the column vector for B. So we get a row vector, complex conjugate of each element, and then when we multiply those together, we get, A1, B1 star, A2, B2 star, and so on and so forth. Okay? For a vector with itself, we mentioned that has to be a real non-negative number. And here we see we have absolute value squared of each element in turn. So here's our first kind of non-trivial thing that we're going to encounter here. One of the things that we say in quantum mechanics is that all state vectors that are proportional to one another are equivalent. Equivalent is probably too strong a word. I'm here in like a math building. This is probably more like a correspondence class than an equivalence class, but we're going to call it an equivalence class. Okay? So what we mean by this is that sometimes I'm not going to worry about normalization. Okay? If you start reading the literature on quantum information science, you're going to see all kinds of state vectors that aren't normalized. It is just one of those things. It is really annoying to write 1 over square root of 2 a jillion times, okay? So the kind of take-home message on this is while I have tried to write it wherever I can, it is not necessarily always going to be true. And furthermore, we can have an arbitrary phase out in front of one of these, right? So by an arbitrary phase, what I mean is that if this is, for instance, a complex number or a negative number, if there is a global phase on the wave function of the universe, there's no way we can measure it, okay? So if I have two operators, for instance, or I should say two state vectors, and they look exactly the same except one of them is multiplied by e to the I phi for some real number phi, we say that those are the same state, okay? These global phases only matter when they're not actually global, which sometimes will occur. Sometimes you might split a wave function into two parts and then you do things with one half of it and not the other half, and you want to keep track of things then. But for the most part, we're going to say that those phases are not accessible via experiment. Okay, so the notation that we've been using is called Dirac notation, right? And we can expand any state vector here in a complete basis of other state vectors. So this is kind of the Dirac notation equivalent of what I showed you earlier, where I was expanding a wave function in terms of the wave functions of stationary states. This is expanding a state vector in terms of a complete basis of state vectors, okay? Here we have this CB is our probability amplitude, just like we had before, right? And it's basically the projection of the vector A on the vector B. Projection, well, you know, if you're trying to picture this, if you're trying to visualize it spatially, you're probably going to have a little bit of a hard time with that because it's a multi-dimensional state space. So I want to discourage you from trying too hard to map this back onto Cartesian vectors and things like that that you're used to. But this is a projection. It's kind of how much of this vector is described by the character of that vector. And the answer is this kind of CB prime. Okay? So the probability for the system in state A to be found in state B is the square, mod squared of that probability amplitude, and it is always less than or equal to 1. Okay, and that basically wraps up our sort of inner product here. Okay, so normalization condition in terms of inner product is obviously that the inner product of a state vector with itself, absolute value squared, has to be 1. Okay, there is something that is quite useful in quantum information called the outer product. And this is getting into the territory where I think this would maybe not be covered for a lot of our undergraduate classes, okay? The outer product of two state vectors, I can make a representation of this in terms of the matrix representation by writing it like this. And our rule for multiplying these is basically given here, okay? This is essentially a definition if you want to take it that way. Okay, so the outer product of a bra with or a ket with a bra, right, ends up being a matrix in our matrix representation here. Okay, so you actually end up sort of increasing the dimensionality of these things when you do this. This we're going to learn later is essentially an operator, okay, that can operate on our state vectors. The outer product of a vector with itself is a projector onto that vector. So this is really useful. If you want to know how likely it is that a certain state provides you with a certain measurement outcome, this is really useful. You can figure out how much of that state is described by the state vector associated with that outcome, and then take the absolute value squared of it to get your measurement result. If you sum over all possible states here, if the B prime is a complete basis here, what you see is that we have the identity operator here, okay? So the sum over these kind of outer products over a complete basis is the same thing as 1. It's the identity operator, all right? And if you have a continuous basis, you need to do it as an integral, as shown here. And that's a really useful kind of math trick, okay? You're trying to prove something or solve something and you have a bunch of bras and kets. You can think about, wait, what if I insert the identity, maybe even multiple versions of the identity into this expression? Sometimes that allows you to actually make some progress forward and make your algebra easier. Okay, so what is all this? I started off talking about wave functions. I then said wave functions aren't quantum states, but I kind of left it there. We can connect back to wave functions by thinking about a position eigenstate. Okay, so this thing, a kind of ket with an R naught in it, represents a completely localized state of the system. It is not a wave function. Okay, what I'm saying is that symbol is the symbol for the state vector of this system if it is completely localized at R naught, right? Which is kind of non-physical. I think you guys know you can't completely. localize something, right, to a mathematically infinitesimal measure, right? However, you may take a more experimental view and say, well, I can localize it further than I care to know further about, right? And in that case, that's what we mean, right? So I'm an experimentalist. I never, there's no such thing as infinity or zero in my world, right? All we ever have is a limit. All we ever have is it's smaller than anything I care about, or it's larger than anything I care about, right? That's really what those kind of non-finite numbers mean. Okay. So now we'll take the inner product of two different position eigenstates, two potentially different position eigenstates. So if the particle is localized at R0 prime, it can't be localized at R0 unless R0 is equal to R0 prime, right? So this gives us a Dirac delta function. This is an infinitely spiky function here that's normalized to 1, all right? And this is a function of position in the sense that we're going to call it a function, okay? Strictly speaking, it's a little bit of a funny one, but we'll call it a function here, okay? So position eigenstates are eigenvectors of the position operator. If I say, what is the position of this thing, or I operate on it with the position operator, I get R0 out in front, okay? So to get to wave functions, what we do is we think about the inner product of some state vector A with the position eigenstate at R0. How much of the state vector A corresponds to the particle being at position R0? That's what that means, right? Okay? Now to turn this into a wave function, I just make it a function, okay? Instead of saying C sub R0, I say this is some function psi of R, okay? So this is the connection between the Dirac notation stuff and the wave function stuff, all right? You take the inner product of a state vector with a position eigenstate, where that actual eigenstate is a function of R, and this gives you the wave function. And to get the complex conjugate of the wave function, we do the conjugate transpose of this expression. Okay? Okay. In a discrete basis, things are pretty similar, but they'll look a little bit different. In a discrete basis, what we have, I mentioned earlier, we can sum over an infinite kind of a complete basis here, all the projectors possible there. And you can define the function of a discrete variable to get a wave function in a discrete basis. So this is psi a of some discrete variable b. B only takes certain values. It's not continuous. But nonetheless, this plays the role of the wave function here. Okay? So if you have an expansion of some state vector in terms of some basis states, you can view the collection of coefficients as a wave function, if you like. It is the same thing. Okay? That's what those mean. All right? Let's see here. In momentum, okay, so this is how we would do the same thing in momentum space. Here we have, to get the momentum space wave function, we take the inner product of the state vector with a momentum eigenstate. Okay? So again, both of them have the same state vector A, but this was an R back when we did psi of R, and now to get, call it 5p or whatever you like, to get the momentum space representation, we do this. To get the whatever, smiley face space representation, whatever you have, right, this is what you do, okay? Yes?
Well, from a mathematical perspective, so R in here, the get R, you're interpreting that as a state of the positions, or what?
Right. That's a state in which the particle is guaranteed to be at position R.
And it's continuous, so basically it's like...
If you allow R to be a variable, then yeah, you can plug in whatever value you want for R there. That's the idea.
And so the wave function is basically just the dot product between these two states. One of them is continuous, one of them is discrete.
Well, I don't know if I'd say that A is discrete or continuous. Maybe discrete, I suppose. Yeah. But you think of, it's basically what you're asking is how likely is it that this state A, if I measure the position, it appears at R, more or less. But you're also retaining some phase information. Oh.
So just for a point of clarity, when I think of the inner product, it's always a number, right?
Mm-hmm.
And so you're just saying, like, this is evaluated at B. This is the number associated with, like, if I look at the bottom psi A of B, that's always a number. Is that correct?
Yeah, I mean, insofar as a function is a number, yeah. Yeah, if we're saying number as opposed to an operator, then yes, it's a number. But it doesn't have to be a single valued thing. We could say, for instance, allow R to be a variable.
Okay.
And then if you want to know what the actual wave function is for position R, you would, some R naught, some particular R, you would plug it into that function. Okay, I don't know how new any of this is. Like this stuff connecting back to the wave function, have you guys seen that before? Has anybody seen that before? A couple of people, yes? Okay, all right. It's not commonly covered for undergraduates, I will say, okay? All right, let's look back at our inner product and try to figure out what's going on with continuous versus kind of Dirac notation here. So if we look at the inner product between A and B, I can do this thing I told you I was going to do, insert the identity. I get to do that wherever I want, right? Okay, so we now integrate over this continuous basis, and I can take this A and bring it in here, right? So I have the inner product of A with R and the inner product of R with B. And what I have here is psi A star times psi B, the integral over that, right? So this is why inner products are sometimes called overlap integrals, okay? So you will sometimes see people write this down and they'll call it an integral. It doesn't look like an integral. And maybe they don't even think of it as an integral, but we call it an integral because there is there are representations in which the way that you compute that is in fact by integrating it, okay? So for expectation values, this is a little bit more complicated, but the actual operators that we have here corresponding to measurement results, which we're going to talk about more in a moment, are abstract when they're written in the kind of Dirac notation here. Okay, whatever this thing is, it just represents, say, position or momentum or kinetic energy, whatever it is, and we can insert a couple of identity operators here. And what you end up getting is that if you can come up with a representation of that operator in the position basis, you sandwich it in between psi A star and psi A in this integral in order to take that expectation value. So if you've seen this before, which you probably have, the connection back here is a little bit tortuous, but you can get there using the same logic as what we had on the left side of the screen. Yes?
What's happened to the D3 R prime?
Delta function at the bottom.
Yeah, that became a delta function. Right? Why did that become a delta function?
Because O is diagonal.
Right,
So
okay,
it's
yeah,
all
that's right.
diagonal.
That was this step down here. Okay. So we said that this is our representation of this thing in the position basis if it's a delta function. Good question. Okay. So back to the Schrodinger equation, all right? Schrodinger equation now we can write with Dirac notation. And the great thing about doing this with Dirac notation is now this state vector, which is this thing that lives in Hilbert space, this abstract space, it can have all kinds of stuff in it. It can have spin in it. It can have all fields, all sorts of mess, okay? We no longer need to think of this as a function of position, okay? It is still the same equation, okay? So whether you think of this as spin or position or a combination of spin and position, it's always just d by dt times I is equal to some constant times the thing again, okay? That's what the Schrodinger equation means, all right? This is not the way that Schrodinger wrote it down, but this is the way we use it in contemporary quantum mechanics, okay? So a matrix representation of this, well, if psi is a column vector here, how do I take the time derivative of a column vector? Well, what you do is you take the derivative of each of these little elements, these CNs here, okay? So this is a way to represent the Schrodinger equation here in terms of this matrix representation of our states, okay? The diagonalized Hamiltonian, so the Hamiltonian operator tells us something about the energy here. It is useful to give it a decomposition that looks like this, okay? So if the Hamiltonian operator times an energy eigenstate, so this state vector corresponds to an eigenstate of that Hamiltonian with energy E sub j, all right? Then you can write it literally as a diagonal matrix, okay? So whether people are actually writing down matrices or not, they will frequently refer to this as the diagonal form, okay, of the Hamiltonian. But you can always think of it represented. This little equals with the dot is always my version of represented, okay? It's represented as a matrix where we have these diagonal entries. Okay, now let's talk about observables and measurements here. So the Hamiltonian was one of these things where we kind of can use it to calculate the energy, right, okay? Well, state vectors are usually labeled with some kind of a label that tells you what the eigenvalues are going to be of various operators. So if it is an eigenfunction of, or an eigenvector of the Hamiltonian, you'll typically label it by the energy. If it is also, or maybe only, an eigenvector of, say, j squared, total angular momentum squared, you'll usually have a little label in there telling you what j is, right? Or what m sub j is, if it's an eigenvector of j sub z, things like that, right? So if we measure the, or if we operate on this state with that operator of which this thing is an eigenstate, we get the value, we get this eigenvalue, pops out in front, okay? But not all legal operators correspond to observables. Those that do, however, are Hermitian. And Hermitian means that if we take the Hermitian conjugate of this thing, we get the thing back again, okay? And Hermitian operators have real eigenvalues, all right? They do not have complex eigenvalues. Okay, what does this mean in terms of our matrix representation? Well, if we take some operator, we can sandwich, just as advertised, sandwich the identity on either side of it. And we can think about expanding this over two different bases. One of them I'm calling rows, and the other one I'm calling columns, okay? We are allowed to move these things around in the way that I've shown you here, okay? Where we retain this quantity here, A row bra, B A column ket, all right? That's this last part here. But this leftover bra and ket can go out in front. And this gives you a convenient way to remember exactly how to work these things out, how to work out the matrix representation of these things. So if you've forgotten which index is the matrix columns and which one is the rows, just try to remember this picture in your head. Sum over the rows, be sum over the columns, okay? And then you can work it out yourself. So that's why we call these matrix elements. You know, these are basically, each of these objects here is called a matrix element because look at this matrix. There are elements in it, all right? When it's written by itself, it doesn't look like it, but when I read it this way, you can see why. Okay. Let's see here. In terms of measurements, B could be a projector. B could be a completely made up measurement, okay? There is no reason why a measurement operator has to have eigenvalues that correspond to something physically attributable to the system. We're allowed to actually assign eigenvalues however we want, believe it or not, okay? So this is an operator I could define. If the state is in energy eigenstate E2, then the result will be a 7, whatever the heck that means. And if it's in state 89, the result will be negative 44, okay? So there's no stipulation here that these things have to be these super well-defined physics quantities, okay? So we will often do this in quantum information where we'll say, well, if it's this measurement result, then we're going to go and do this thing over here. And if it's this one, that corresponds to a whatever, a 1 or a 0 or a whatever it is, okay? So you can assign those eigenvalues however you want. The way projective measurements work is that we use this probabilistic interpretation. So if the system's not in an eigenstate of whatever our measurement operator is before the measurement changes the state, okay? And we end up with an eigenstate of the measurement operator after the measurement. Now, the annoying thing about this is that we don't have any control over it. We aren't able to force the particular outcome that we need. This is completely probabilistic as far as we know. So aside from calculating the probabilities of obtaining various measurement results, we don't believe there is any more information hidden in the system that would allow you to actually predict with more certainty what the outcome is in a given single-shot measurement, okay? So this is kind of a digitization step. This is super important in quantum error correction. In quantum error correction, the state of the system before you measure it and the state of the system after you measure it are completely different. And the fact that you ended up in an eigenstate of the measurement operator is actually really, really useful because it allows you then to do things to correct for errors that have occurred, all right? That part is missing in classical analog computing. Okay, so let's talk about expectation values. In a classical probability, they also use expectation values, if you weren't aware. And the expectation value of some quantity B here is basically the sum over the measurement outcomes times the probability of obtaining each measurement outcome. This is fancy talk for an average, okay? In quantum mechanics, it's just a little bit more complicated because we don't have right away these kind of probability amplitudes. What we have instead are the wave functions. And so here I'm going to do the same thing I keep doing again and again. We're going to put the identity operator in here. We can sum over our complete basis, okay? And what we get is that we have, for the expectation value of this operator B, we have a sum over all possible outcomes for it times the probability that we obtained that outcome, okay? You can work through this using just sort of all the stuff that we already covered, but this is sort of the well-known result. Okay, for a single shot measurement, this is where we're going to encounter one of our first sort of subtleties associated with measurement here, okay? So in a single shot measurement of some observable that yields the measured value B, what do we learn? And by single shot, I mean I have one system, I prepare it in some state A, I then perform a measurement of this quantity denoted by B, and I get some value for it, okay, lowercase b. What have I learned? Just about all I've learned, more or less, is that the state has a little bit of character of the B eigenstate in it, okay? I actually haven't learned a ton, okay? If we measure multiple identical copies in the same way, we gain more information, all right? And there are two common approaches for doing this, and the differences between these two are going to be really important for the talks you're going to hear by Nick Chilton and Nick Hutzler. And so here are the two possibilities. One of them is we're going to measure an ensemble average. So if I have, for instance, a lot of copies of the system available, I'm going to measure the average of all of those outcomes. The other possibility, which sounds the same at first, is a little bit different. We are going to average each individual copy and then, or we're going to measure each individual copy and then take the average of the whole thing. These sound the same, okay? But there are some important distinctions here, okay? So you're going to measure the value B bar of an ensemble of n identically prepared systems, or you measure an ensemble of individual outcomes, all these B's, from n identically prepared systems, and then we take the average. I'm not going to jump right to why these are different right now, but it's really important, okay? So if you have some system that you have like a beaker of stuff and people are saying they've got qubits in their beaker, okay? You can say, well, but you have access to the individual qubits. That's kind of the difference here, okay? All right. Crazy talk. You can't ever measure a wave function. You guys ever heard that? Nobody's heard that?
Yes.
Okay, yeah, right? You can't ever measure a wave function. This is something that I feel like I hear a lot, all right? And here if we have, it's in a pure state, which we haven't even talked about, but that's kind of a detail, if I have infinite copies, okay? Well, a wave function is just a bunch of expansion coefficients, okay? And you can measure expansion coefficients, you can measure a wave function, all right? Somebody might gripe and say, well, you're not measuring it directly, but I would turn around and say, when was the last time I measured anything directly in the lab? You never measure anything directly, okay? We always measure some quantity. We have a model. We describe our model, how it corresponds to the thing that we're interested in. And nobody loses any sleep over it. But if you say you're going to measure a wave function, sometimes people get really upset, okay? But you can absolutely measure a wave function, all right? No problem, okay? You can measure those coefficients. You can measure their phases. That is what a wave function is. You can measure it, okay? So I'm going to give that 3 theorist beam splitters, all right? There's a little bit of truth in it. A wave function is not necessarily an observable, right? But for the most part, I say that's bunk. We can do this. Okay. Let's see here. We're at 40 minutes. Okay. In your chemistry education, if you took chemistry quantum mechanics, you may have encountered the spin 1/2 operator, which looks like this. We write it as a vector, and here my kind of unit vectors here are these E hats with subscripts on them. And you were probably told that it obeys this algebra here, right? Okay. We have the S squared operator, which is convenient because it is a simultaneous eigenstate with one of the projections of the spin. The eigenstates of this, and this is where those of you who took all this stuff in physics might get a little, it might look a little unfamiliar to you, but they're called alpha and beta, I think commonly in the chemistry. Is that fair, chemists? Alpha and beta, right? Okay, all right. Here we go, alpha and beta, okay? So if you say you measure the square of the spin of alpha, what you get is 3/4 h bar squared times alpha. That's an eigenstate, all right? Beta has the same total spin, but they have different z projections. So alpha is called spin up, and beta is called spin down. And this is the kind of well-established notation there. Okay. Convenient in this business is always to do raising and lowering operators. So these are our ladder operators. If you try to raise the spin up state, you can't do it. If you lower the spin up state, you can, right? And we end up pulling an h bar out here for these, okay? In terms of Neo and his spoon, we can represent these as column vectors with 2 entries. These are called spinners. Spin-ors, okay? And anytime you see a representation like this, whether people are talking about spin or not, they will often call them spinners, okay? And so if we want to compute these things that we already talked about, like for instance, what is the norm squared of alpha? Well, we can do this now with our little matrix representation and get the same thing. We get 1, right? It's normalized. Same for beta squared, right? And we can do an inner product here between the two. It's the same as the other inner product. And so any pure state of our spin 1/2 system here can be written as 2 coefficients, C alpha and C beta times these 2 column vectors, which I could write in my spinner representation as a single column vector with those 2 things as the entries. Okay. Well, up and down aren't the only possibilities, right? We also can think about spin along x, right? And spin along x would be given in this thing by alpha plus or minus beta. And to show you that that's true, you can think about representing everything in terms of the matrix representations here. Here, this is the SX operator written as a matrix. And we have our spinner here. And what we get is that this is indeed an eigenfunction of SX. Likewise, we can do the same thing along the y direction. Notice that there are h bars always popping up here. This is a real spin. This is a real angular momentum. Okay, this thing is really a generator of rotations. Okay. All right. Here's a crazy talk claim. Spin is super quantum mechanical because the operators don't commute. Okay, that's another one I've heard before, right? And people will even talk fancier about it a little bit. Okay. All right. They say, oh, that's quantum mechanical. You have these non-commuting operators. Well, I mean, there are other things that don't commute, okay? People knew about things that don't commute well before quantum mechanics was invented. Things like rotations in 3 dimension are a good example of a system that has operators that don't commute with one another. If I rotate some 3D system around x and then y, it's different than if I do it first around y and then x, right? Don't watch that in slow-mo. I didn't do my hands right for it. All right. Also just like the polarization of like a laser beam, if you want to describe that, you use the exact same algebra, okay, as we do for spin. All of these things, all of these operators and things that I just mentioned, map 1-to-1 on it in terms of the algebraic properties of those things. So that's all SU2 if you know what SU2 is, okay? So I'm going to give that 3 Theorist beam splitters as well, all right? That's pretty wrong, okay? It's important in quantum mechanics that the operators don't commute, but it's not a very quantum mechanical feature in the sense of not exclusively quantum mechanical. Okay, we're done with real spins. Let's talk about qubits, okay? This is our smallest element of a quantum computer, of a processor, of a quantum simulator. It's a bit, right? It's a 2-level system, and somehow or another, this is what we're going to build everything up from, okay? From here on, I'm probably going to work in units where h bar is 1, by the way, so if I write a Hamiltonian, it's going to have units of frequency, okay? So what we do is we define a qubit subspace that is spanned by the Z eigenstates 0 and 1. These are the two states of our qubit. We say that 0 is the +1 eigenstate of the Z operator, and 1 is the -1 eigenstate of the Z operator. That will bother many of you because it sure does look like 0 has a higher energy than 1. And if you're used to writing the energy as the label of these things, that's going to bug you. It bugs the heck out of me, but it's conventional. There are good reasons for doing it this way. And if we try doing it the other way, we're going to get lost. So this is the way everybody does it, okay? In terms of matrix representation, we have our spinor representation here, right? So we can think of 0 as being spin up and 1 as being spin down, if you want to think of it that way, okay? We can write an arbitrary pure state as a linear superposition of our two basis states. And you've now seen this about 14 times in this talk, right? This should not, I think, be a big surprise to you. And we have the normalization condition associated with the fact that if this is going to be a legal state vector and we say it's normalized, we require the abs squared, sum of the abs squareds of those coefficients to be equal to 1. Now this is very helpful, this last part here. We can always write a pure state of our qubit in this form. So cosine of some angle theta over 2 times the 0 state plus e to the I phi sine of that same angle theta over 2. And our stipulation here is that theta spans from 0 to pi and phi spans from 0 to 2 pi in this representation. What this is a geometric representation of the pure quantum state. It's called the Bloch vector. You will notice theta and phi here, and it may make you think, well, what if I have polar coordinates, or spherical coordinates, I should say, right? In spherical coordinates, theta is typically this kind of angle from the vertical, and phi is the angle from the x-axis, if you will. And so this provides us, if we take all of our state vectors and we write them in this form, just by finding theta and phi, we can figure out where this blue Bloch vector lives on the surface of this unit sphere called the Bloch sphere. And this is a very helpful thing for visualizing what happens in quantum systems. It will mimic the actual direction of real spins in some cases. Real spins in real space. However, this is not real space, this is abstract space. Okay, if the vector points up here, okay, that means that it is in the +1 eigenstate of the Z operator. If it points to the south pole, that means it is in the -1 eigenstate of the Z operator. Okay. Let's see here. What about other states other than the north and south pole? So if theta is pi over 2. Then we're on the equator, right? Somewhere in the equatorial plane of the Bloch sphere, okay? And if phi is 0, we will get that this state is 1 over root 2 times 0 plus 1, right? Here we had cosine pi over 4, which is 1 over root 2, plus e to the I 0 times sine pi over 4, which is another 1 over root 2. And this is our x eigenstate, okay? So this was the thing we met before, the spin x eigenstate, right? Here's our qubit version of it, and it points along the x-axis of the Bloch sphere. You might say that's how we define what the x-axis of the Bloch sphere means, okay? It means that this state is exactly pointing along it, right? And the -x state will be kind of back there. So this is one of the cases where, you know, I want to really be clear about this. When you talk about whether two quantum states are orthogonal, or you start talking about projections of quantum states on one another, be careful, because if you think about the Bloch sphere, you might see things that are at 90 degrees from one another, yet they have a non-zero, the quantum states have non-zero projection on them, okay? Don't try to apply projections and things of quantum states to the geometry of the Bloch sphere. You'll get yourself in trouble. Orthogonal states are antipodal on the Bloch sphere, not 90 degrees from one another. They're 180 degrees from one another, okay? All right. What about operators and the Bloch sphere? Well, we talked about the Z operator, and I've sort of alluded to the X operator. Here, they obey the same algebra that we had for our spin operators, okay? Yes?
Just to recapitulate, is that I usually work with this, the Pauli matrices. Your spin 1/2 operators is H bar. h bar over 2, these ones?
That's right.
Is minus h bar over 2.
I think plus h bar over 2 times these.
And alpha will be the ket 0 and beta will be the ket 1?
I don't know.
If not, it doesn't really matter.
I think alpha is 0, yeah, I think. You should double check me though. Let me know if I got it wrong.
No. It's just like I don't usually use the other ones.
Okay.
I use these ones.
Cool, all right. And we met some of our eigenstates already. Plus and minus x are just 0, plus and minus 1. Plus and minus y eigenstates, what points along the y direction of the Bloch sphere? Well, it's 0 plus or minus I times 1. Okay. We can't have simultaneous eigenstates of non-commuting operators. Those would be incommensurate observables. And so we can't have a simultaneous eigenstate of x and y, right? Okay. Or x and z. We kind of always, if you have an eigenstate of one of these Pauli operators, it is not an eigenstate of any of the other ones, okay? The matrix representation of this is the Pauli matrices. So you have probably seen this before. Here, we're not having h bars or 1/2 or anything like that. The Pauli matrices have kind of unit entries in them, okay? So the z, you might call this sigma z if you've ever seen that as a Pauli notation, sigma x and sigma y. And then of course we have the identity here. Okay. All right, all of the Pauli matrices are unitary, which means that if we take m dagger m, it has to be equal to 1, where m is a Pauli matrix. And they are Hermitian. They are actually equal to themselves. So the square of a Pauli matrix is equal to the identity. They also have a determinant of -1. Okay. The Pauli matrices times I form a basis for a group of unitary matrices with determinant 1. That is called the special unitary group, SU2. Okay? Unitary operations are reversible, and so they conserve probability. And this is a little proof of that we can walk through quickly. Basically, as long as you require that the expectation value of the identity here is equal to 1, then you can show yourself that these actually have to have m dagger m is equal to 1, okay? Otherwise, we don't conserve. Basically, we require that we conserve probability, so if you undo an operation, right, after you do it, you have to get the same thing again, right? This chunk here has to be equal to A. Okay. The expectation value of a Pauli operator, the exponentiation of a Pauli operator might be a little bit frightening. So now I'm taking some abstract thing and I'm putting it at e to the power of that thing. Or maybe if you think of it as a matrix, it's something complicated. Well, just remember that we could define this function e to the x in terms of its Taylor series, if we wanted here, okay? And if we do that for this operator m, we can expand that. Now, remember that m squared is equal to the identity for a Pauli. So we'll get alternating objects that are proportional to the identity times something that's proportional to Pauli. Identity, Pauli, identity, Pauli, alternating. Okay? We can gather all the terms that are proportional to the identity operator into one part of a sum, all the ones that are proportional to Pauli, to a single, Pauli to the 1th power as the other one, and this allows us to write it in this form here. Okay? This is incredibly useful, all right? This is basically just as useful as our writing the identity and inserting it into our expressions here. You exponentiate any of those Pauli operators, e to the I theta over 2 times y, e to the I theta over 2 times x, whatever it is, you can write it as cosine theta over 2 times the identity minus I sine theta over 2 times that Pauli operator. Okay. Let's see here. There are other useful Pauli operators. Linear combinations of x and y sometimes get used. You might see this called sigma sub phi, but it's nothing more than this. So this is like a Pauli operator that you can think of it, it's somehow confined to the equatorial plane if you want to think of it as living on the Bloch sphere. The phi just tells us where it is compared to the x-axis. The Pauli vector is going to be very helpful for us. This is a vector of Pauli operators. If you want to think of a matrix representation, it's a vector of matrices. That sounds scary, but it's just this, okay? It's really not that scary. We just have a unit vector in the x direction times the x operator. Unit vector in the y direction, y operator, so on and so forth. Okay? Remember this? Like if you're scared of this Pauli vector, I say, why weren't you scared of this? Okay, these are the same thing, all right? Note that if we take the dot product between the Pauli vector and some unit vector, n hat here, we can get some operator. And so if n hat here lives in the equatorial plane, which is to say that if n hat is described by this bottom equation, then we have this upper thing, that sigma vector dot n hat was equal to sigma sub phi. All right? There are also ladder operators, just like we did with spin. Okay, we can make non-unitary raising and lowering operators for the qubit. So x plus iy is basically an operator that takes you from the 1 eigenstate to the 0 eigenstate, which we called raising. Remember, 0 is the positive valued eigenstate of the z operator. Okay, the lowering operator is just x minus iy over 2. Okay, in terms of matrix forms, these are like this. And so you can see that these are actually not going to be unitary. Okay, if you take the square of one of these, you're not going to get the identity matrix out of this. But these operators are nonetheless fairly useful for us. Okay. So what happens to the Bloch vector as we do quantum operations on it? Okay, let's consider an example. The prototypical example here is that if we have a Hamiltonian where we have, it's proportional to a Pauli vector. So here, imagine we have our spin, and there's a B field in the n hat direction. This would be the form algebraically that the Hamiltonian would take. All right? We somehow have an energy shift associated with the direction of the spin compared to the B field, what its projection is along the B field. Okay? If you think back to the Schrodinger equation here, and we plug this thing in, what we have fundamentally is something that looks like this. The time derivative of a thing, smiley face, is minus I times some constant times the thing again. And you know that when you see a differential equation like that, e to the minus I times that constant times time is usually what you find that smiley face is proportional to. Okay? So I'm not proving anything to you here, but it may not surprise you to learn that if we make the time evolution operator, u of t, this is a function of time, and it takes psi at t equals 0, and it returns the state of the system at time t, that it is basically just you exponentiate the Hamiltonian. So this was why it was helpful for us to do exponentiation of a Pauli. When I say exponentiation of a Pauli, psi vector dot n hat counts. That is also a Pauli operator. Okay? As long as this n hat is real valued, right? That works. Okay. This thing is called the propagator or the time evolution operator. And if we look at that exponential expansion that I gave earlier, you can start to see what's happening here geometrically. It's a rotation operator. It rotates the Bloch vector about the plus n hat axis through an angle given by omega t. So if n hat was in the x direction, then psi vector dot n hat would just be x, the x operator. What this does is it rotates the Bloch vector about the plus x direction, out of the screen. Okay? And the degree of rotation, how far it rotates, is just given by omega times time. So this is how we use our Bloch sphere. We have a vector that represents the state, and the operations that occur almost always are given by rotations on this thing. All right? Unitary operations are all given by rotations. Okay, so we have some direction n hat. We rotate the thing about that n hat direction. So let's do some examples. What if it is in the z direction? Well, here would be kind of like a magnetic field in the z direction. And so our time evolution operator is just cosine omega t over 2 times the identity minus I sine omega t over 2 times z. Okay? And what this does is it takes, if for instance, if we started in an x eigenstate, what we get is that it rotates it about the z-axis. Okay, this was what I was going for here. All right, you can work through the algebra to see what happened here, but we have a little bit less of plus x, which is what we started in, and we're starting to pick up some minus x. What we're doing is rotating that thing around there. Z rotations are associated with the phase of the system. So phase shifts and z rotations, I want you to start equating those in your head. By phase, what we mean is the relative phase between 0 and 1 in a qubit. Okay? And one of the ways to see that is to imagine, okay, well, let's take the evolution operator associated with some z rotation. And what we get here is, in our matrix representation, a thing that looks like this. So if we apply that to some state here, what we're going to find is that it pops up right here. Okay? This is where we're going to get our phase. Okay? The physical picture for what's going on here, which is important in our physical implementations, is that since the time evolution operator is the Hamiltonian exponentiation of the Hamiltonian in cases where it commutes with itself at all times. Okay? That means that if you have the energy between the 0 and 1 state in your system fluctuates, changes a little bit, you're going to pick up a phase error. Okay? So a good qubit is one that has a really well-defined energy between the 0 eigenstate and the 1 eigenstate. Okay? So if you say I have a physical system and I'm going to make it a qubit and it's like super magnetically sensitive, that's going to stink. Okay? It's going to stink because there are magnetic fields everywhere and the energies are going to be going and you're going to have a lot of trouble keeping track of it. Okay? There's a lot of magnetic field noise. This phase is quickly going to become something that you no longer know. So one of the criteria that we have, and the end of my second lecture goes over kind of formalizing those criteria a little bit. One of the criteria we have for our qubits is going to be that they have a really well-defined energy relative to one another. All right, that's a key feature. Okay, so we're getting into more and more quantum computing language here. Let's talk about some operations that you might use in a quantum computation, pi rotations. Okay, if I rotate through an angle pi, okay, about the z-axis, all right, I would call that, first of all, any rotation through an angle pi is called a pi pulse in this language. This comes from kind of NMR, all right? When I look at what this expression turns into, well, we're going to have cosine of pi over 2, which is 0, right? And then we have minus I sine pi over 2, which is 1 times z. So rotation through pi about the z-axis gives us minus I times the z operator. That is the evolution operator associated with it. So we're going from a description where we said, oh, this is what happens as a function of time. Now what I'm saying is, well, the thing, gets applied and now it's done. How do we describe the result? Well, we can describe it as if this just operated on this state. Okay, we don't need all the in-between data points of what happened as a function of time because we know what the total evolution did. It became z here. Okay, so we rotate half a turn about the z-axis, whatever that Bloch vector is. The same is true for the x and y directions. These give us a group, okay? This is the single qubit Pauli group. So the single qubit Pauli group consists of the Pauli operators times plus or minus 1 and the Pauli operators times plus or minus I and the identity minus the identity and the identity times plus or minus I. This forms a group, okay? And you can kind of convince yourself that it's closed by looking at a few examples, right? If it's a group and x and y are elements of the group, then when I multiply them, I'd better get another element of the group, and sure enough, I do. Minus iy, z is x, and x times ix is I times the identity. Okay. All right, now that was our pi rotations. What about pi over 2 rotations? We don't necessarily always want to do the same thing. A pi over 2 pulse is also possible, and this would be like a quarter turn, okay? And if you look at what that does, for instance, about the x-axis here, I can take the time evolution operator associated with it, and I find that when t is done here, that accumulated angle is pi over 2, and what I get is that we get, well, it's just algebraically we have 1 minus ix, okay? This will take, for instance, the minus y eigenstate to 0. So minus y eigenstate is back here. I think I have a picture. And it goes to 0 and back and forth. So actually, this operator does the opposite. This operator takes the 0 state and goes to the -y eigenstate. It takes the 1 state and goes to the +I eigenstate. So if we look at the trajectories here, the south pole goes to this location right there. The north pole goes to that location at the antipodal point there. Okay? And that is, as advertised, a rotation about a quarter turn about the x-axis.
So exponentiating the Pauli matrices give you an arbitrary rotation inside of the Bloch sphere.
That's right.
But if you apply the Pauli matrices by themselves, that's equivalent to a pi rotation.
You've got
about that axis.
Yes, times minus I. That's right. You've got it.
Right in the phase. Yeah.
Yep. If you care about the phase, you don't always care. Precisely. Yeah. Okay, so when we're doing pi/2 rotations in our quantum circuit diagrams, we'll sometimes write it as, this sort of a notation, Rx of pi/2. If we're doing rotations by pi, we will almost always just write it as x or y or z or whatever the axis is. Okay, unless it's about some weirdo axis. Okay. Another possibility here is, let's see here, that we do about the y-axis. In this case, 0 gets taken to the +x axis, or the +x eigenstate, and 1 gets taken to -1 times the -x eigenstate. Okay, so here the north pole comes down here, the south pole goes up there. Okay, and that's a rotation about that direction. Okay. Let's see here. There is an alternative picture where people refer to the Bloch sphere itself as rotating and the Bloch vector as staying fixed. Just be aware, it's kind of active versus passive conventions for rotations. I think this is the more common one. Okay, here we say we rotate the actual Bloch vector. Okay, there is another operation that is a pi rotation, but it's a little bit funny. It's called the Hadamard. Okay, the Hadamard operation takes the 0 eigenstate to the +x eigenstate. So what does that do? And the 1 goes to -x. So that looks like a rotation by pi/2 about the y-axis. Okay. Then it also takes the +x eigenstate to 0. Okay. The -x eigenstate goes to 1. So we kind of follow that by a pi rotation, if you like, here. Okay, and some phase. All right. It is also possible to write this as a pi rotation about a tilted axis. Okay, and that tilted axis is 45 degrees between the x and z, +x and +z axes, all right, times a phase. So this is another way to think about what the Hadamard operation is. You rotate by pi about that axis, and then there is an overall phase shift. The reason this is useful, let's go back. The reason this is useful in quantum computing is that it takes you between z and x eigenstates, basically. That's how that gets used. So if you want to put a qubit in a state that is a superposition of the possible basis states with equal probability, Hadamard is a good way to do it. Okay. Phase gate is another one we are going to encounter. And the action on basis states here is that it doesn't do anything to the 0 eigenstate. The 1 eigenstate goes to I. And we go between +x + y and -x - y here. Okay? So the phase gate is basically the square root of the z gate. Right? This is called the S gate. All right? It is essentially a pi/2 rotation about the z-axis instead of a pi rotation about the z-axis. Okay, or sorry, yeah, all right. There is also something called the pi/8 operation. All right, this is called a T-gate. It is the square root of the S-gate, if you will. Okay, it's an even smaller rotation about the z-axis. All right, here square root of I is e to the I pi/4, and this is just an even smaller rotation about the z-axis. It's essentially a pi/4 pulse about the z-axis.
So square root in the sense that it's half the rotation.
Yes, but also if, for instance, you take the positive square root of the matrix representation, it will actually be the same thing. Yeah. So I think algebraically that is actually true. Yeah. Okay. all right. Now we're going to get into multiple qubits, which is where I wanted to kind of finish the talk today. So what I'm trying to get to here is give you some flavor for how a quantum computer is powerful and why it's powerful. And to do that, we have to talk about more than one qubit. So let's talk about product states. Now, you probably learned how to do quantum mechanics with the hydrogen atom. Okay, so forget about the electron spin. This would be like the first attempt at writing down the Hamiltonian for an electron in a hydrogen-like ion. And here, one of the first things that you probably encountered was the idea that we're going to break up the wave function into a part that is radial and a part that is angular. Okay? What you're doing here in terms of the quantum state is something called a tensor product, also known as fancy time symbol. Okay? A tensor product is basically telling you that you have things that live in different spaces. They are, in this case, you have separable degrees of freedom in your system. The angular wave function kind of lives in a world of its own compared to the radial wave function. Okay? We are going to simplify this. All that means is like keep track of labels. That's what that means. Okay? So it just means keep track of your labels. So if you have labels corresponding to qubit 1 and qubit 2, secretly you're doing a bunch of tensor product stuff, but you don't have to write a bunch of fancy time symbols. And in fact, people, probably myself included in this presentation, use it a little too much in cases where it actually isn't even needed. Okay? So if I have 2 qubits and I have an X operation on only one of them, how would I write that out? Well, what we call this X sub 1, all right, and here I'm operating on a state vector associated with 2 qubits. What we do is we say that this is the tensor product of the X operator with the unit, with the identity for the other qubit subspace, okay? So this is the identity operator of the appropriate dimensionality for being the identity on just the subspace for the second qubit. This is our X operator for the subspace of the, well, this is the X operator, okay? And it is a 2x2 matrix if you do a matrix representation of it here, okay? And so really, you know, kind of the way to think about what is happening with that tensor product is that it kind of lives like that, okay? Likewise, if I have an operator that operates only on the second qubit, you can think of that as secretly being this thing. We have the identity operation on the first subspace, qubit 1 subspace, and we have the X operation is going to go on the qubit 2 subspace. Okay? If we have 2 qubits, how do we write the states? Well, let's imagine that we have the 2 states given by this, A and B, with their coefficients A0, A1, B0, and B1. Oops, I have a little funny thing with my appropriate displaying of my animation. Well, A tensor B, right, which we would also write as just one ket with A comma B, or AB in it, right? What this is it's A0, B0 times 0, 0, right? 0, 0 means qubit number 1 is in the 0 state, qubit number 2 is in the 0 state, right? Plus some amplitude for 0, 1, which is A0, B1, so on and so forth. In terms of the matrix representation, it would look like this column vector. It's now a 4-entry column vector. So we had 2 qubits, okay? We're going to have 2 to the n entries in this vector for n qubits, okay? And this particular thing that's going on here, that fancy time symbol corresponds to something called the Kronecker product of those 2, okay? For operators, if we have 2 operators that look like this for single qubits, okay, we can make the tensor product of those 2, all right, using our, you know, kind of the rules that I've given you here. It's actually very, very lengthy, okay, to go through this, but we essentially go through every permutation of the basis states here. And the appropriate coefficients, if you just look at the subscripts, they follow exactly what is going on with these ket bras here, okay? The full thing looks like this, all right, if you care. All right, you almost never need to like work this out. You will get a computer to do this, okay? But that's what that means, all right? So the Kronecker product, if you want to think about what this looks like in terms of a matrix representation instead of this bra-ket abstract thing here, what you do is you take the first matrix and the first element of it and you multiply it by the entire second matrix, Okay? That is the top left four entries of the resulting matrix that represents the product of the tensor product of the two operators. Then you do the same thing over here, same thing over here, and same thing over there. So what you get is this thing. All right? So this is how we make operators that have, some aspect of them that is operating on qubit number 1, which would be the first one, and qubit number 2, which would be the second one. And this generalizes to as many qubits as you like. Okay? The important thing to think about here is just to remember that once we start carrying around labels, we no longer need to worry about what order were these things multiplied in when we have something like that, right? If we just label them, then we can use normal multiplication. So an operator, remember, an operator just for one subspace, let's go back to this just a second, just for one subspace really is tensor product with the identity, okay? So if I think about tensor product with the identity here, in this expression, you can tell I'm just going to get, well, M00 on the diagonals, right? M01 on these diagonals, M10 on these diagonals, and M11 on those diagonals. Okay? So when we say M1, M sub 1, M operating only on qubit number 1, what we always mean is that it's M tensor identity. Okay? It's actually an operator with the full rank of the space, right? However many qubits you have, it is that large. It's that many by that many if you want to think of it as a matrix. Okay? It's just that all the other qubit parts of that thing are the identity. It doesn't touch those parts of the space. Okay. If you want to code this thing up, it is helpful to think of it like this. So if you have more than 2 qubits, what you're going to do if you want to make an operator that operates only on qubit number j is you'll sandwich it between a Kronecker product. You have identity for all of the qubits where k is less than j, and then you'll do a Kronecker product with all the qubits that are larger than j. If you're not coding it up, that's not all that helpful, but just in case you're trying to write down your code, that'll be helpful for you. Okay. All right, single qubit Paulis in a 2-qubit system. I told you that x1 was going to be x tensor 1, right? So in terms of matrix representation, we have 0, 1, 1, 0. That's our x. That's the blue things. And then the gray things, each of these is going to be multiplied by the 2 by 2 identity matrix, and we get this thing. Okay? If we have it operating on qubit number 2, we do something else, right? We have the identity, 1, 0, 0, 1. And then each of those elements is multiplied by the x operator, and you get a different matrix, right? As you should, okay? So this is how we think about, whenever you see this x1, it is not a 2 by 2, it's not represented by a 2 by 2 matrix. Implicit in the fact that there's a subscript is that it has the size necessary to operate on the entire Hilbert space, okay? And the way it does that is there are secret identity operators in there, but people sometimes don't write them, okay? For the Y and Z operators, these are here. And again, my slides are available on the shared drive for those who want them. Okay, how we do? All right, we're doing okay here. All right, here's the big finish. Quantum computing. What's the deal? Why is this helpful? Okay, think about 3 qubits, or 3 bits, 3 classical bits, okay, which I could also write with this Dirac notation. If I have 3 classical bits in a state like this, or 3 qubits in a state like this is called a product state. Each qubit is described by 2 coefficients, A and B, right? Or theta and phi, if you like, right? If you want to think about Bloch sphere coordinates. A, B, C, D, E, F. I have 6 coefficients needed to describe this state. That's it, okay? If, however, I allow the system to explore the full state space allowed by quantum mechanics, I allow states of the form of this, where I can have independent coefficients here, as long as it's normalized and things like that, right? Okay? All right? This is a 3-bit entangled state. And an entangled state means that I can't decompose it as a product of individual qubit states. Okay? The number of coefficients here is 8. All right? This does not sound like a big difference, because it is not. 6 versus 8 is not a very big difference. The point is that this scales like the number of qubits. A classical state and a product state scales like the number of qubits. An entangled state is exponential in the number of qubits. And it doesn't take many qubits before this difference becomes quite important. So if you imagine that you have 200 qubits, then the number of coefficients I might need to describe a product state is 400. And the number I might need to describe a full quantum state, right, is, this goes around, right? It's like, okay, all right? This is just like astronomically huge. You'll never do it. You can't do it with your classical computer. So somehow at the bottom of all this, and this is not the full story, and it's a great discussion to have, it's a question I think about a lot. Somehow at the bottom of this is the idea that this quantum device can access this enormous amount of memory. That we could never even enter data in or even get data out of that many bits in the memory. But somehow during the computation, it's allowed to use this enormous amount of memory. So the way a quantum computer beats a classical computer is essentially that the classical computer runs out of memory. It's not really a processor speed thing so much as a memory thing. All right, I'm being a little loose with this, but that's kind of like the take-home message here. Okay, this is why this stuff works. So the black box version of what a quantum computer does is that we start with a bunch of individual qubits here. And the number of things I need to do classically to actually encode that is a polynomial in the number of qubits, or really just linear in the number of qubits. So that I can do, even if n is 200, no problem, right? I can prepare 200 qubits. At the end, I'm going to measure the state of those same qubits, or maybe even just a subset of them. Again, it's linear in the number of qubits. It's 200 measurements. I can do that. Somehow, during the algorithm, this thing is using this much memory, okay? It has access to an exponentially large space in which to do all of its quantum-y stuff, all right? And that's how we end up getting there. Okay, last thing. This was going to be optional, but I think I have time, right? Okay. So here's my connection to chemistry, thanks to Justin's books that he lent me. All right, there's a subset of gates called Clifford gates, okay? The Pauli group, you remember we introduced here, all right? Those are the elements of the Pauli group. Clifford gates take Paulis to Paulis, all right? So if C is a Clifford gate, then C times a Pauli times C dagger, right? Basically, we rotate the Pauli operator using the rotation operator C is in the Pauli group again. Okay, that's called a Clifford gate. All right? There are 24 elements of the 1-qubit Clifford group. And I am not going to have time to tell you why the Clifford group is important, but it is important in quantum error correction. Okay, this is a place where people think about it a lot. The elements of the Clifford group are things that take Paulis to Paulis. So what sorts of operations can we do here that take basically these frames and create a new frame that is contiguous with the old one, right? Okay. Well, rotations by pi about the three, x, y, and z axes. That one's easy, right? If I do that, then any Pauli eigenstate gets moved to another Pauli eigenstate, right? Okay, rotations by pi over 2. About the same things. We've also got that, right? So now we have 1, 2, 3, 4, 5, 6 of these operators. These, by the way, you can arrive at these by doing the exponentiation, right? E to the minus I pi over 4 times ex, e hat x is going to give you this. Okay. Rotations by 3 pi over 2 about ex, ey, and ez. Okay. So here we have minus sign essentially in front here. All right. Then we have rotations about pi, or by pi, about axes that are kind of halfway in between these. All right, it's getting a little more complicated, but we can do that. All right, so here we had 1, 2, 3. Here we have 2, 4, 6 more. Okay. Then we have rotations by 2 pi over 3 about the axes that are kind of halfway between each of the 3 principal directions. Right? We can do those. Okay, and we get how many of those? We get 1, 2, 3, 4 of those. Right here, the plus minus subscript 1 and plus minus subscript 2. I'm just trying to say that those plus and minuses are independent of one another. That's all I mean there. Okay? And then we can do rotations by 4 pi over 3, about the same thing. We just pick up a minus sign there. And the identity. Okay? That is the single qubit Clifford group. It has 24 elements. Here they are. I was furiously writing this down in my office right before I walked down here. Okay? I think that's them. I might have a mistake in there, but that was my best guess. Okay? Now these operations that I did on this sphere, for those of you with a chemistry background, you may have thought of something else that has the same symmetry, which is an octahedral molecule, right? Like SF6, or even a cubic molecule. Okay? This has the same sort of symmetries as the Clifford group, right? And in terms of the notation that you may be familiar with from PChem, all right, this is called OH, the octahedral group here. There's one center of symmetry, 3 C4 axes about X, Y, and Z, 4 C3 axes about these kind of axes that are halfway between all 3 of them, 6 C2 axes about the axes that are 45 degrees from those things, 3 planes of symmetry perpendicular to the principal axes, 6 planes of symmetry perpendicular to X and Y, and the identity. Okay? And so it's different language, it's talking about different operations, but fundamentally at the heart of it, if you are familiar with the kind of group theory from PChem, it may help you to get a more tangible grasp on some of the things that we're talking about. Okay, I think that we need a break. So let's take a break, and please work on your origami during the break if you have time, because we're going to use this thing when we reconvene, what, in half an hour? Yeah, 11. 11, okay.